All right, so day 2 of applications rates of change. Value of a postage stamp, V in dollars, is modeled by this function. It's a square root function, 100 times the square root of t, and the square root stops. That's not a typo or anything, plus 1 at the end. T is time in years. Determine the instantaneous rate of change of the value of the stamp at 100 years. So you should know how to solve this. There's nothing different about it, really. It's just, again, slightly different functions. The math works out slightly different, the algebra. So, but you can go ahead and get started, and if you get stuck, then we'll help each other along. So go ahead. Okay, I didn't see anybody have an issue with this, but when you find the value of the function at 100, it's 1001. I think from what I saw, nobody messed up there. That is something, although it's simple, a mistake that people do make. And then here's what I've done so far. So I start with my formula. I subbed in the function at t and the value of the function at 100 on top here. And then just simplify 100 times the square root of t minus 1,000. I saw a lot of people were at that step and even going forward because most of you know what to do. So what do we do at this step? So this question is actually like the learning goal that we did that we haven't taken up yet, but I have it here, so we'll take it up when we're done. And most people did very well. In fact, it was done really well. And so square root functions don't seem to be a big deal. People know what to do at this case. And that was even one where you were given the slope of the tangent, we're finding a point. So, you know, it's a little bit different, but people still didn't have a problem. But at this step, what do I do? Yeah, very good. Over itself, right? Because so I'm going to multiply by 1. But I'm going to show you something. And this is just personal preference. But again, you know, it's interesting to see algebra done slightly different ways. That top part is factorable. Yes? So if you didn't do this and you've already gone past it, that's fine. You don't have to go back. I don't know if this makes it easier or anything, but sometimes smaller numbers are easier to work with. And again, this is just, I mean, this is where mathematics is going if you continue to take math courses, is the specifics of the algebra are very personal. They're different. It depends on the question, depends on how you do it. It's always going to work out no matter how you do it, as long as you don't make mistakes, obviously. But, you know, do you factor? Do you not factor? It's not a matter of a rule that you do in this case or you don't in this case. It's what's convenient, what works for you. How do you see the problem being solved? Okay. And then in this, and the only good thing about this is, so in this case, what do I multiply by? I multiply the square root of t plus 10 over the square root of t plus 10. Like the 100 part becomes irrelevant. Some people might have thought, don't you have to multiply by everything? But you don't. Watch. It'll work out. Okay, so I'm going to pause here again, and I'm going to let you either continue from this step or continue from where you were. See how the math works out. A few people on the learning goal didn't show this, and you must. So we'll talk about that when we take it up. But you should be showing what you're doing. They just went from this step to the next step, and magic happened. Show me what's happening here. Don't make me assume that you multiplied by a conjugate. And so a couple of people multiplied by something that wasn't 1 here. Like you multiplied by this or something again. Like you multiplied it by itself, like you're squaring it, which A is not going to help, and B is you can't do that. You can't just square one side of an equation and not the other. So you got to make sure that you, and we talked about this on Friday, that you are multiplying by 1, because that's what doesn't change something. So it's not always necessarily going to work out that easily, but when we factored in the first place, in this case, it ended up meaning we didn't have to factor in the end. So, it kind of worked out nicely. Numbers were smaller, easier to do in my head. Those are the benefits maybe of factoring. But I ended up getting t minus 100 here, which just divides to 1 right away. And I get 100 over the square root of 100 plus 10. So the square root of 100 is 10, plus 10 is 20. This is 100 over 20, which is 5. And if we go back to the original question, said the value of a postage stamp is modeled by the function, by the square root function we worked with, t is time in years, determine the rate of change, instantaneous rate of change of the value of the stamp at 100 years. So what does 5 mean in this case? Jason? $5 a year. So not a ton, but
After 100 years ago,
yeah, absolutely. And it's a stamp. So one stamp increasing by $5, that's not bad if you have a stamp collection, I guess. I don't know. Okay, we good? Okay, example 3. So you'll recognize that this one has to do with volume of a sphere, and there were a couple of questions in the practice that were like this. And there's no reason why people wouldn't have been able to solve this, except maybe in the end your answer didn't match, or there is a step where you might have gotten stuck. So we'll take a look and see how things work out. So a balloon that's a perfect sphere, which is not really realistic, but anyway, is being inflated. The volume of the balloon is modeled by the equation, that's just the equation for volume of a sphere, where r is the radius in centimeters. At what rate is the volume of the balloon changing with respect to radius? We'll understand exactly what that means at the end. We'll come back to that. If I forget, try to help me remember. When the radius is 10 centimeters. Okay, so this is not with respect to time, though. It doesn't give us anything in terms of the speed of that at which the air is flowing in or anything like that. Okay, so that's why it's with respect to radius. It's a little bit different. In the end, it ends up meaning something important. So we're going to find the value of the function at 10 centimeters. And so here's a trick to these. We're going to leave this answer in terms of pi. We're not going to try to get the like rounded answer. Now this is something that if you've never seen it before, you might think, well, how am I supposed to know that? Well, I mean, if we had more time, then I could push you to think this through yourself. What's the process that we're going to go through following this first step? Well, we're gonna use our difference quotient, and we're gonna sub things in and start doing some algebra, and then eventually we're gonna factor so that we can divide. Well, if you have a rounded answer here, do you think it's gonna factor properly? Probably not. Our general rule is, well, not probably not, it won't. Our general rule is that we only round in the end. So we haven't really talked about this when we used to do answers in terms of pi back in the first 2 units when were doing trigonometry. We sort of took it for granted, but we didn't say this. But I would say almost universally, if you are doing something that involves pi, you keep the pi symbol so you have an exact value until maybe the very last step. Depending on the final answer, you may round or you may not. Okay? But we almost always work with a number in terms of pi, whether it's trigonometry or anything else, measurement or anything. We keep the pi symbol, we do not round. Okay, when we're doing any kind of algebra or, when we're not just finding the volume of something, that's typically what we would do. So if you don't fully understand what I mean, it'll make more sense in a moment once we get through this. So slope of the tangent equals the limit as r approaches 10 for the volume given radius minus the volume at 10, for r minus 10. Okay, and so you may want to watch because this step will be almost identical every time you do a question like this. Not every question is about a sphere. There are other shapes where it would be very similar, but the specifics would be different because the formula is different, like a pyramid or a cone or something like that. A cone would be in terms of pi, a pyramid would be different, right? But there are other shapes. But in this case, and the two from the practice, it's basically the same, where at this point I'm going to common factor, and I'm going to common factor. Again, this is another reason why we want the pi in here. I'm going to common factor the pi out, and I'm also going to factor out the 4 over 3. So if I take out 4 over 3 pi, I'm left with r cubed, and I'm left with negative 1,000. In fact, I can go back to this step right here, and I can see that, I multiplied these two together to get 4,000 over 3, and then I just divided the 4 over 3 back out and got back the 1,000. Maybe it would have made even more sense. We could have seen it better if I had left my answer like that, but at the time I had no reason to do that, right? And then what do I have here? We should recognize this from earlier in the unit. Difference of cubes. How do you do a difference of cubes? So you take the cube root of this, which is r, the cube root of this, which is 10, and this first bracket shares the same sign, which is useful because that's the bottom part there. And then this is the first term squared. This is the second term squared, so 10 squared. And this is the first term times the second term, 10 times r. And this sign is always positive. This sign is always opposite of that sign. That's the pattern. Go back and look it up and remember it if you want to from our lesson so long ago. And there we go. Those divide to 1, which is what we were looking for. So now I've got 4 over 3 pi times r squared plus 10r plus 100. Any questions? Let me just sub in. Ten times 10 plus 100. So this is 100 plus 100 plus 100. And I'm going to do this. 300 divided by 3 is 100. and I get 4 pi times 100, which is 400 pi. And so then the last little bit is, if you did these questions, you notice the answers were written in terms of pi, like the pi was still there. That's how that all works out. And again, that's typical. There's no reason to round that answer. And then we say, therefore, the volume is growing or increasing or changing by 400 pi centimeters cubed per centimeter. Not per second, not per day, not per month, not per year, not per minute. It wasn't per time. It was with respect to radius. So as the radius is changing, the volume is changing. What speed, what rate is the radius changing? I don't know. That's not what this question is about. And to do that actually requires quite a bit more work with this stuff. You would solve questions like that in calculus, but not in this class. So we wouldn't be able to do a question like this in terms of calculus. You can think about this a little bit. If you don't quite get it, just try to remember that a question like this would be centimeters cubed per centimeter. But it's 400 pi centimeters cubed volume per centimeter change of radius. So as the radius changes, the volume changes is what that unit is saying. It's a rate. So you're right. It almost looks like could you change that to centimeters squared? No, you wouldn't, because it's a rate. So we're showing both units. It's like meters per second, but the rate is centimeters cubed per centimeter of radius. So you would leave it the way it is. And you could have a rate of any 2 units you want. Like, there's no reason why you couldn't have rates that don't involve seconds. It's a different kind of rate. It's not a speed rate. We tend to think of them as speed because we often do those, but you can have all kinds of rates. You probably saw different kinds of rates back in grade 9. I mean, dollars per kilogram, right? Like, that's a rate. You pay a certain amount per kilogram of apples or whatever, right? At the grocery store. Any questions?